And we're on part 3. It's the muscle tissue, particularly related to skeletal muscle. And let's check it out here. We're actually in chapter 9 now. And we have this view right here that we were looking at. It's a little, how shall I say, more focused on the myosin and the actin. Okay? And this is where the action is. They're calling the actin here, as you can see, the thin filament. Do you see that? It's really actin. And the thick filament over here, it's really just a whole bunch of myosin. Okay, so in here that we're actually taking a look, we're going to get a up close and personal look at myosin. What you've got here is your basic golf club, except that it's paired. And it's got a little helical wraparound. Okay, but it's got this long sort of like shaft. Then it's got this folding, flexible, we call it the hinge region. And then we have a head on both ends of the molecules here. Now the head is, in fact, an enzyme, and it's ATPase. It is the enzyme that both synthesizes and breaks down ATP. Okay, you need to put that inside your hat right now, because that's going to be the basis of everything. We also have very specific binding sites here where it binds to actin. So high specificity, it likes to bind to actin. You know what it likes to bind to even more than actin? Hundreds of times more than actin? It likes to bind to ATP. That's its fave. Okay, that's the cheesecake of ATPase, is ATP. It loves it. Okay, then you put a bunch of these together and you get a thick filament after you put all of these together that looks like this. Then over here we have actin. Actin comes in little subunits, globular subunits, that can be polymerized by bonding to each other. And when they polymerize, they make these nice long little polymers. They're little threads, and we put a couple of them together and we wrap them around each other in a nice helical arrangement. And then, and this is where, you know, the lingerie aspect comes in. Do you notice, look very carefully, this is a moment of detail here, that we actually have this little sort of like this little thread here. It's called tropomyosin. You see that word right there? Tropomyosin. It's pointing to the little orange bikini that covers the little binding sites very carefully. Isn't that cute? And it also has little clasps here called a troponin complex. Okay, so you can actually take your bikini off, as it were, put it back on again, just the way you like it. And you have to use the little troponin complex to do that. And you know how you move the little tropomyosin away from the opening here on the actin is you mix calcium ion into the solution, the fluid around here, the cellular fluid. It binds to the troponin, and the troponin actually changes conformation or shape, and it draws this tropomyosin off of the binding sites, those little openings there. Okay, and that's how we initiate a contraction, is that we send calcium into the cytoplasm of the muscle. All muscle works this way, all of it, right? And so it's something to consider. Calcium, pretty important molecule. Okay, so we'll come back to calcium for its importance on many occasions. Okay, who is the heavy hitter for nutrient value of nutrient density? It turns out to be spinach and broccoli. Who'd have thunk? Popeye was right. Anyways, the deal is that the tropomyosin is covering that. Now let's. There's going to be a story that I'm going to be telling you about, and so I need you to pay very close attention here. Here they sort of summarize everything in a table, so that you're sort of with the program. Okay, so here they've revealed that the thin filament is actually actin, and the thick filament is actually myosin. Okay, now we know the truth. We know the truth about myosin, and we know the truth about actin, what's really going on. Okay, so you can only begin to imagine the stories that I'm going to be telling very shortly. So here we have a bunch of myofibrils together in a muscle cell arranged, and what they're doing here is that they're trying to show us, first of all, the sarcolemma. The cell membrane is right here, right, just the way you like it. And you'll notice that the cell membrane has an invagination right here. Okay, this is called the T-tubule. I need you to pay close attention to this, because the nerve is going to stimulate the muscle. It's going to send an action potential to the muscle. It turns out that the muscle cell has the same capability as the neuron, and it can carry that action potential just as well as a neuron along its sarcolemma. It's got the technology for it. Okay, and that once you get to this spot or this spot, it's actually going to penetrate. The action potential is going to go inside. Once you're inside, you have this elaborate ER, endoplasmic reticulum, which, of course, they're not going to call it ER. That would be too easy. No, they're going to make up a new name. Okay? And so they're going to be referring to it as the sarcoplasmic reticulum instead of endoplasmic reticulum. Sarcoplasmic reticulum, just the way you like it. Okay? So what do we have here? We have a mitochondria. Why would we have mitochondria? Because they make ATP. Lots of ATP. Who likes ATP? Myosin likes ATP. Right? So right here, this is this is the cheese factory right here. The cheese the cheesecake factory or whatever. It's basically it's making all the goodies for over here. Alrighty, so we have the T-tubule coming in, and it's connecting over here with these little how shall I say these? These are cisterna of the sarcoplasmic reticulum. These are little holding tanks here. And what are they holding? They're holding calcium. Okay, so that's where we keep our calcium. And if we need calcium, then we release calcium because the action potential has come through here. It says contract, and the calcium is released, and everybody begins to contract. Okay? So that's the deal right there. And we give it a name, of course, because it's a triad. It's three things. It's a little, it's the terminal cisterna of the sarcoplasmic reticulum on either side of the T-tubule. So cisterna, T-tubule, cisterna, just the way you like it. Okay, here they actually have, I used to have a graduate professor in in cell and molecular biology, where he used to say, and we have pictures. He used to always say that, Dr. John Stubbs, and we have pictures to prove it. Right, he was always into that. So here we have actually a sarcomere at this length, and it's the same sarcomere now. It's shorter. Look at that. It actually, we had binding, and we had the head turning, and we pulled the little actin filaments together. It's very exciting. Okay, so so here's the deal. Here is the neuromuscular junction, and we're not at a place now where I can really talk about this with any depth, because I haven't taught you enough yet to really learn about action potentials. But nevertheless, notice that calcium comes in here, and because calcium comes in as a result of the action potential coming down, then we have neurotransmitter. And again, it's calcium that causes neurotransmitter to enter the synapse and to bind to the little sodium channels here and get the action potential to continue in the muscle itself. So that's an important detail. Okay, now I'm going to be cutting to the chase here pretty soon. Okay, but here again, another little version of calcium coming in, neurotransmitter. Who's the neurotransmitter? It's acetylcholine. Acetylcholine comes down. All skeletal muscle uses acetylcholine. Okay, so that's all you really need to know about that. Acetylcholine enters the synapse. It binds to the far side, and we have the action potential crossing over from the nerve to the neuron, rather, to the muscle cell. And we're going to just continue that action potential, and that's what that's about in the cell itself. Okay, and here's yet another picture that tells you that, and we'll pick up the action in our next part.